Hello everyone, in this video we are going to go through a paper of Paul-André Melliès called Higher Order Parity Automata. The objective is not to explain all the details, but to try to understand the objects that are manipulated and the kind of result we can get in the domain. The paper introduces the notion of higher order parity automata, and therefore the main result is the following. The problem that is, given a higher order parity automaton A and a finite lambda item m of same alphabet and type, then the question whether the automaton A accepts the Böhm tree Bt of m is decidable. So we are going to travel all around the world of theoretical computer science, where it is possible to find the infinitary lambda calculus, higher order automata, residual theory, and the lambda y mu nu calculus. So let's go, in and out, 30-minute adventure! Here is the wonderful land of infinitary rewriting, and I am standing in a strange place where piles of snow are defined either by induction or by co-induction. A pile of snow is a stack of snow where there is a top. A finite inductive pile of snow is exactly what you think it is. Start from the ground, you add snow until you are tired, and the top is on the top. A finite co-inductive pile of snow is defined from the top, under which you add snow until you are tired. So one can just say, okay, I put the top on the floor, I add snow until I am tired, and then I reverse the pile of snow, so it is a normal pile of snow where the top is on the top. Or one can just look upside down and consider that the top is on the floor. To build an infinite inductive pile of snow, you start from the ground and you add snow infinitely. So there is no top in this structure, so it's not a pile of snow. However, an infinite co-inductive pile of snow can be constructed because the top is on the floor and you add snow infinitely. So there will be no ground, but since there is a top, it is a pile of snow. So these kinds of infinite objects cannot be built inductively but co-inductively. End of this introduction. So first, let's define by co-induction the untyped infinitary lambda term. In this more complex example, co-induction is the reverse of induction, where instead of building bigger and bigger objects from base cases, you have an object and you say of what it is composed. You look how to plunge deeper and deeper in it. The rules for building untyped infinitary lambda terms are the same as for finitary lambda terms. Note that a branch of an infinitary lambda term may be infinite and therefore may have no lead. Using a special set of variables called a nominal set, we have the result that an infinitary lambda term has a finite number of free variables. However, it is possible to have an infinite number of bound variables, and a free variable may occur infinitely many times. Let's now define the simply typed infinitary lambda terms. Like in class, the types are defined by the grammar, where a type is either the ground type O, A times B, A arrow B, or 1, which is a kind of neutral type. We now get to higher order alphabets. It's called higher order because higher order automata are mainly used in higher order model checking, which is model checking in orders higher than the first order. So a higher order alphabet is a finite alphabet sigma, just like with normal automata, and a function bold sigma that assigns a type to each letter. And in a tree, the type of a letter gives its arity. It's quite like a ranked alphabet. For example, if A is of arity 2, then its type can be O times O arrow O. Or if B is of arity 0, then its type is just O. And like in the lecture, to give a type to a lambda term, we use a typing derivation tree. A typing judgment is composed of a higher order alphabet, an untyped infinitary lambda term, and a simple type. Typing derivation trees are defined like in class, with the variable the abstraction and the application rules. But here it is by co-induction, and it's snowing too much, so we are leaving this place. To define the notion of reduction, we introduce the same notion of occurrence as in the lecture, that will describe finite position on the infinitary lambda terms. We also introduce the prefix relation on occurrences of an infinitary lambda term m, denoted like this. The convention for beta redexes is going to be quite different. For any occurrence O of a lambda term m, there exists a context CMO made from m where there is a hole at position O. By denoting MO, the subterm of m after the position O, one can write that m is equal to the context CMO evaluated in MO, as depicted in this magnificent text drawing that falsely represents an infinitary lambda term. A beta redex is then defined as a triple MON, where m is an infinitary lambda term, O an occurrence of m, and n equals MO. The beta redexes being defined, we are going to see how to have an infinitary beta reduction path. Consider the graph whose vertices are the infinitary lambda terms of type A, and whose edges Mn are the beta redexes MON. The depth of a beta redex MON is equal to 1 over 2 to the power of the size of O. The depth of a finite path is the maximum depth of the beta redexes composing it. All the infinitary beta rewriting paths are not going to have interesting properties. We are only going to consider what are called strongly convergent beta rewriting paths. Those are the normal beta rewriting path in infinitary lambda calculus. A infinitary beta rewriting path MO to M1 and so on is strongly convergent if and only if for any integer n there exists a rank n of n, after which, for any finite path from P to Q, its depth is smaller than 1 over 2 to the power n. We are now able to present a result that will be useful in a moment. It's called infinitary subject reduction. It says that if one has a beta redex MON and that there is a typing derivation of sigma entails m is of type A, then there exists a typing derivation of sigma entails n is of type A. But this was only subject reduction. Infinitary subject reduction is a generalization to strongly convergent beta rewriting path. We suppose here that there is a strongly convergent beta rewriting path from m to n, and that there is a typing derivation of sigma entails m is of type A. Then there exists a typing derivation of sigma entails n is of type A. So it's time for us to leave this beautiful place I like so much. But don't worry, we still have plenty of other places to visit, and I'm sure you won't be disappointed.
Here is the lush land of finitary and infinitary trees. It's beautiful, but in order to avoid problems when talking about tree automata, we must get quite far from the trees. Because just like French policemen, the trees are afraid to be recognized. First, let's define a pre-ordered set of ground states. But before, a little reminder. A preorder is a transitive and reflexive binary relation. Now suppose given a preordered set of ground states, QO square subset O, then any simple type A induces a preordered set of higher order states of type A. In order to simplify the notation for the arrow rule, let's define an intermediate type Bang A. Its set of states is the set of finite subsets of QA, and the subset A1 to AM is smaller than the subset B1 to Bn, when all AI is smaller than a bj. Then the set of states of type A arrow V is the Cartesian product of the set of states of the type bang A and the set of states of the type B. This preorder is the Cartesian product of the inverse preorder of type bang A and the preorder of type B. We don't need to define it for the product type because we will write it and interpret it as arrow types. Now, before defining higher order automata, I think it is important to have a view of finite tree automata to have a smooth introduction. A bottom-up tree automaton is the data of Q, a finite set of states, F, a ranked alphabet, which means that the letters are given an arity, I, a set of initial states, and delta, a set of rules that assigns a n tuple of states to a state and a letter of arity n. The idea is that when the automaton reads a node f in some state q, then the rules tell in what state the automaton will be when reading the children. It starts at the root in an initial state and ends in the leaves. Higher order automata are defined similarly. A higher order automaton is the data of QO, a finite set of ground states, sigma, a higher order alphabet, which takes the role of the ranked alphabet, A, the simple type of the automaton, Q0, an initial state of type A, and delta, a function that associates to each letter a finite set of states of the type of the letter. We can extend the preorder on states on a preorder on automata. First, let's extend it to a preorder on transition functions. Let delta and delta prime be transition functions of the same alphabet sigma. Then delta is smaller than delta prime if and only if for all letters A of sigma, delta of A is smaller than delta prime of A in the finite set preorder on states. And the preorder on automata is just going to be a combination of the preorder on states and of the preorder on transition functions. Let A and A prime be automata of the same alphabet, same type and same states. Then A is smaller than A prime if and only if the transition function of A is smaller than the transition function of A prime and the initial state of A is smaller than the initial state of A prime. This being defined, let's now see the acceptance condition of a higher order automaton on an infinitary lambda term. For this, we must define what is the run of an automaton on a lambda term. The run of an automaton is described as a tree called run tree. As you can see, the root of a run tree is of the form the higher order alphabet sigma unfolds an infinitary lambda term m of type A using a transition function delta and in the state q. The rules are introducing a variable, applying the abstraction rule, applying the application rule, and there is also a rule introducing an infinite tuple of run trees. Note that the last rule, called infinite bag, allows to have infinite branching run trees. So an infinitary lambda term m is accepted by a higher order automaton A equals q sigma A delta q if and only if there exists a run tree with root sigma unfolds m of type A using the transition function delta n in the state q. Before leaving this beautiful place, let's see an interesting result justifying the introduction of the preorders. Let A and A prime be higher order automaton of same alphabet, type and states such that A is smaller than A prime, then if A accepts an infinitary lambda term M, we have that A prime also accepts M. So now it is time to leave for a new place. I'm very happy to have been able to bring you here, and I hope you enjoyed this little sailing with me.
There is something constant in this city. It is the depressive calm coming from those rainy nights. This calm, this gloomy environment, enables to put in context time and space, and to discover what is invariant in these. Numerous poets like Pierre de Ronsard, Charles Baudelaire, or Didier Super came here to get some inspiration. Nothing surprising then that lots of invariance theorem has been invented here. The first part of our invariant theorem, the forward preservation theorem, is the easier part. If there is a strongly convergent beta rewriting path from M to N, and that a higher order automaton A accepts M, then it also accepts N. The idea is very similar to a previous result we have mentioned. To see this, let's unfold the definitions. A accepts M if and only if there exists a run tree having as root sigma unfolds M is of type A using the transition function delta and interstate Q, and is the same for A accepts N. So the forward preservation theorem is a sort of translation of the infinitary subject reduction, but in run trees instead of typing derivation trees. The forward preservation theorem being explained, let's move forward. The second part of our theorem is more difficult and requires introducing more objects. So let's extend the notion of occurrence to the notion of diffraction patterns. If M is an infinitary lambda term, we define the set of diffraction patterns of type A by induction on A. The set of diffraction patterns of M and of the ground type is exactly the set of occurrences of M of the ground type. The set of diffraction patterns of M of type A arrow B is the set of occurrences of M of type A arrow B plus more strange objects that are a set dA of diffraction patterns of type A that multimaps a diffraction pattern of type B. And because we want to be able to use this form like an occurrence, let's define what's called the head occurrence of a diffraction pattern. The head occurrence of an occurrence is, well, itself. And the head occurrence of a diffraction pattern of the form dA multimaps dB is the head occurrence of dB. To make a link between occurrences and strict diffraction patterns, they can be seen as trees where occurrences are the trivial tree. The tree defined by a diffraction pattern is called its shape. The shape of an occurrence D is the trivial tree with only a root labeled *D. The shape of a diffraction pattern of the form dA multimaps dB is the tree shape of dB, where the root of dB is connected to all the shapes of the elements of dA. This really shows that diffraction patterns are an extension of occurrences. Now I will make a fast introduction to residual theory and then extend it using diffraction patterns. If R is a beta redex MON, then the residuals of R, denoted R between brackets, is a relation between the occurrences of M and the occurrences of N, and it must satisfy some properties. The self-destruction, which says that there is no couple of the same occurrence. The finiteness, which says that the occurrences of M are related to a finite number of occurrences of N. Yes, when I write an element and then the residual relation, it represents the elements that are in relation with the first element. It's some kind of composition. A residual must also satisfy the finite development property, which says that there are no infinite paths using only residuals of M, and the local confluence property, which says that two co-initial reduxes of R can always be reduced to the same term. And one can also compose multiple residual relations to obtain a relation on beta rewriting path. So this was the classical residual theory using occurrences, but here we use diffraction patterns. Again, let R be the beta redux MON, and let D be a diffraction pattern of M. The diffraction patterns of N, which D is in relation with, is defined by induction on D. If D is of the ground type, then it's an occurrence, and its residual relation is the classical residual relation. If D is of type A arrow B, and if D is an occurrence, then its residual relation contains the classical residual relation, and also a diffraction pattern dA multimaps OB, such that D equals OB.body, and dA contains the occurrences of the variable that is going to be replaced by the application rule. If D is of type A arrow B, and if D is a diffraction pattern dA multimaps dB, then its residual relation contains the copies of D where its head occurrence is duplicating using R, and also the unique diffraction pattern d'A multimaps d'B, such that d'A is the set of diffraction patterns of N that are related to an element of dA, and d'B is the unique residual of dB along R. After that huge and complicated definition that I allow you to forget right now, let's use strongly convergent beta rewriting path and make symmetry between run trees and typing derivation trees. As with classical residual theory, one can compose a residual relation on a rewriting path, and a strongly convergent beta rewriting path between M and N induces a residual relation between the diffraction patterns of M and N. If you remember well, the set of diffraction patterns have been defined by induction on the type, and a type is a typing derivation tree, so it is possible to do the same with the run trees, and therefore it is possible to define a residual relation on run trees. A run tree R of the infinite real lambda time M induces a residual relation between the diffraction patterns of M and R. And well, let's move a bit. Now, thanks to the residuals, we are able to give the idea of the proof of the forward preservation theorem. This reciprocal is called the backward preservation theorem. It says that if you have a strongly convergent beta rewriting path between M and N, and that N is accepted by an automaton, then M is also accepted by the automaton. To justify the long definition of the residual theory we just introduced, let's see how those are used in the proof. An occurrence of M induces a set of diffraction patterns of N by using the residual of the path, and a diffraction pattern of N induces a set of diffraction patterns of the run tree of N, Rn. And a diffraction pattern of Rn induces a state of the same time as MOM, where OM is the occurrence of M. Therefore, an occurrence OM of M induces a set of diffraction patterns labeled by the states of the type of MOM. It's here that we use the fact that run trees may have infinite branching. By using the infinite bag rule, we can combine all the diffraction patterns of OM, F, Rn to create a run tree on M. So now that we have our forward and backward preservation theorems, we can combine them into our preservation theorem. It says that if there is a strongly convergent beta rewriting path between M and N, then a higher order automaton A accepts M if and only if it accepts N. Therefore, to check if an automaton accepts N, it is only necessary to check if it accepts M. And I know it's very calm and gloomy here, but we have to move to our last place. It's very sad that we are a bit late on time and I am absolutely frozen, so I am going to take a great shower. In the game The Witcher, the player has to make decisions, and therefore it is the perfect place to deal with decidability theorems. It is now time to tell you how to build infinitary lambda terms. For this, we are going to use a derivative from finite lambda calculus called lambda y calculus. A lambda y term is built just like lambda terms, but also includes the term y, which is a fixed point operator. This means that a lambda y term lambda n can be unfold reduced to n yn. So, to generate infinitary lambda terms, we'll apply this unfold reduction rule infinitely many times. This way, the term obtained is not an infinitary lambda y term, because the y disappears, since it is at the ground which is infinitely far in the term. If m is a lambda y term, denote by m infinite the infinitary lambda term generated by unfolding y in m an infinite number of times. There is a first decidability result about infinitary unfolding. It is the following. Given a higher order automaton A and a finite lambda y term m of same alphabet and type, then the question whether m infinite is accepted by A is decidable. To understand more what the unfolding of a lambda y term is, I have a little example. This is the tree representing a lambda y term. The y is not at the root, so everything before it will stay as such in all unfoldings. You see that the term applied to y is a lambda f something. Then the structure will repeat itself using this variable f. Applying the unfold reduction gives the tree in the center, where on the left the subtree n is almost the same, with the exception that f is replaced by f prime. On the right, you have exactly the original tree from the application on y. To see how the structure is repeated around f, one must apply a beta reduction rule on f prime. Now we get a tree where the subtree n has been lifted to the top, and the original tree has been repeated at the occurrence of the variable f. It is now time to introduce another concept that is in the main theorem we are trying to prove, the Böhm trees. A Böhm tree is defined by co-induction on the grammar containing the normal form of a term or a constant. So each infinitary lambda term m has a unique associated Böhm tree denoted bt of m. Also, if m is a lambda y term, denote by bt of m the Böhm tree of the infinitary unfolding of m. Furthermore, there exists a strongly convergent beta rewriting path between an infinitary lambda term and its Böhm tree. And since the acceptance of an infinitary unfolding is decidable, and that there is a strongly convergent beta rewriting path, then by using the invariant theorem we get our first decidability theorem. Yes, the previous one doesn't count. Given a higher order automaton A and a finite lambda y term m of same alphabet and type, then the acceptance of the Böhm tree of m by A is decidable. You just test the acceptance of the infinitary unfolding and it gives you the result for the Böhm tree. And we're leaving this place because it's too noisy here. It's better here, isn't it? So, you may wonder why my bodyguard is a witcher, and that's none of your business. And you may also wonder why I didn't say that we proved the main theorem. Well, it's because the main theorem is about higher order parity automata. So, we still have more definitions to introduce. An infinite path is a sequence of occurrences following each other. It means that On plus 1 is On concatenated with body, fun or arg. Denote by infinite path of M the set of infinite path of M. Yes, that's an ambiguous name because there is no S at infinite path. A boundary of an infinitary lambda term M is a subset of infinite path of M. Boundaries are often denoted with the letter thorn, which, as you know, is an ancient English letter. Then an infinitary simply typed lambda term with boundary is a tripole composed of an untyped infinitary lambda term M, a typing derivation upsilon, and a boundary thorn. I hope you are very happy with lambda y calculus because we are going further. Behold the lambda y mu nu calculus. Well, in fact, it's not much harder. A lambda y mu nu term is exactly a lambda y term, but here there are two types of fixed point operators. Y mu is an inductive fixed point operator, and y nu is a co-inductive fixed point operator. Lambda y mu nu terms are linked to boundaries thanks to the following proposition. A lambda y mu nu term m induces an infinitary lambda term with boundary. The unfolding of m and its taking derivation are going to be exactly the same as with lambda y terms. The difference is only going to be in the boundary. Each fixed point operator generates a specific kind of path. I depict here the shape of the infinite unfolding of m. On the right there is an infinite sequence of application nodes, and on the left there is the repeated part of m. The inductive operator y mu generates paths that explore a finite number of app nodes on the right and then finishes in a repeated term. The co-inductive operator y mu has the path exploring a finite number of app nodes like y mu, but also the path exploring only the app node on the right. So only this infinite path makes the difference between the inductive and the co-inductive fixed point operators. Let's now define the path of a Böhm tree. If there is an infinite beta rewriting path between m and n, then a path of m is necessary to a path of n when it is necessary for its computation. So we can use this definition to build a boundary of the Böhm tree using the boundary of m. By taking the path of n such that all paths of zone n are necessary to them, we get zone n, the boundary of n. And this defines the boundary of the Böhm tree. It leads us to our second decidability theorem. Given a higher order automaton A and a finite lambda y mu nu term m of same alphabet and type, then the question whether the Böhm tree generated by m is accepted by A is decidable. And well, it's too hot here, so let's go somewhere colder. It's beautiful, isn't it? But it's the last part of our trip, where we are going to define the notion that is in the title of the article, the higher order parity automata. But first I will introduce the word parity automata and then the tree parity automata. An omega automaton is an automaton on infinite words with a set of acceptance conditions, which is a set of infinite sequences of states. A run of an omega automaton generates an infinite sequence of states, which are the states that the automaton takes during the reading of a word. Parity word automata are a special case of omega automata, where the states are the integers from 1 to k, and the acceptance sequences are the sequences where the least state appearing an infinite number of times is even. For example, if only the states 2 and 3 appear an infinite number of times, then the automaton accepts. However, if 1 appears an infinite number of times, then the automaton does not accept. In a parity tree automaton, all the paths from all the branches must form an accepted sequence. We are about to use the decidability of higher order automata on lambda y mu nu terms to prove the decidability of higher order parity automata on lambda y terms. For this, we are going to create a translation of lambda y terms to lambda y mu nu terms and of higher order parity automata to higher order automata, by creating k copies of the same thing for some rules in order to translate the parity aspect. Let omega be the set of parities, which is the integers from 1 to k, and one can suppose without loss of generality that k is odd. Let square be the k-fold operator such that square of a is the k-fold product of a. The translation of the types is going to be the following. The translation of 1 is 1. The translation of the ground type O is O. The translation of A times B is the translation of A times the translation of B. And the translation of A arrow B is the k-fold product of the translation of A times the translation of B. For the translation of terms, we use the fact that a lambda y term is beta eta equivalent to some term y lambda f p, where p is a lambda term not containing the operator y. The translation of p when P is f of the type A and sigma unfolds P of the type A, is f1 is of the type A to fn is of the type A, and the k-fold product of sigma unfolds the translation of P of type of the translation of A. And the translation of M is k fixed point operators alternated of the translation of P. And before the last theorem, a result justifying this translation, a higher order parity automaton A with a higher order alphabet sigma and type A is equivalent to the higher order automaton translation of A with a higher order alphabet translation of sigma and type translation of A. And now, beware Meliuz Theorem. Given a higher order parity automaton A and a finite lambda item M of same alphabet and type, then the question whether the Böhm tree generated by M is accepted by A is decidable. This trip was truly fun, wasn't it? Okay, well, I hope you have enjoyed this little trip with me, and even though you won't remember any precise thing from this presentation, I hope that you have been able to have an overview of what can be done in infinitary rewriting. It is now time for questions, but please understand that I had to make efforts with the form because I am not so much at ease with the content, and I may have said some false information. Anyway, I let you with me of the present, and I hope that he will be nice to you because he is going to die, whereas this presentation is not. Thank you.